So slightly different approach now. So who has heard about decoding or MVPA? Is it that acronym that ring a bell to some of you? Okay. Who thinks he knows what it means? Hopefully me.
You mean the acronym or what it actually means?
Oh, the acronym, because there are multiple versions of the acronym.
Multivariate pattern analysis?
Multivariate, the fMRI people recalled it multivoxel pattern analysis. So we can do multi-channel, so MCPA for MEG. But the idea is So the fundamental idea to understand is it's also a non-parametric approach. And the idea is to say, if there's an effect in my data, I'm supposed to be able to learn it from a fraction of my data. And if you give me new data, which are supposed to be independent from the data I used to learn, I should be able to predict above chance. Okay. So give me data, for example, you have data with a certain evolution over time. If I know the past, can I predict the future? Okay, that's all these machine learning approaches where you basically have an estimator, a classifier that can classify new data based on the past. Okay. So what people have used it for in fMRI is basically give me your fMRI data and can you predict what the subject was doing, what the subject was viewing given the bold time courses or just the beta map from the GLM. So we can use this type of approaches with MEG, and the big benefit of MVPA or decoding is to leverage the information from all the channels and all the time points to increase the evidence. Somehow it shares a lot of ideas with cluster level analysis where you try to improve your statistical power by looking at the neighboring time point, the neighboring frequency, and extract more information by this notion of cluster. Okay. So here, when you do this decoding or MVPA approaches, you need two things. You need to define what classifier you will use. So most people would come up with the same solution. So if I ask you to pick up a classifier, what will be your answer? What's the number one classifier that people like to use because it's fancy?
Support vector machine.
A support vector machine. That's okay. So the support vector machine has multiple variants. So it's known as a kernel method. But at the end of the day, everybody uses a linear kernel. And what it means is that if you give me data, let's say if you have 306 channels, you have a topography is a vector in a space of size 306. Okay. So I'm in a space of 306 dimensions. And if I have got topographies in one conditions in this space, which are just points in this big space, I've got this set of points for condition A and another set of points for condition B. Can I fit an hyperplane that will separate my two clouds of points to discriminate between condition A and condition B? More or less clear? Okay. So now if you take all the channels and you take all the time points, you have 306 channels and 100 time points. Okay, you have 306,000, take 1,000 time points. You have 306,000 dimensions. You have all the topographies over the entire time. And that's going to be your one data point. Okay, so it would be one trial. And given a set of trials in condition A, in this huge space, can you find an hyperplane that separates my trials in condition A to condition B? And now if I give you new trials, can you predict from each of these trials if it's A or B? Okay. It's non-parametric in the sense that you derive statistical power by just predicting on new data and not by looking at the distribution from given an hypothesis about the statistical properties of your data.
Is that clear? That's a really good point.
Basically, if you're able to predict something you've never seen, you've learned something. It's not by looking at a table in a distribution that you say, okay, that's an extreme point, so it's very likely to be a real effect. Okay, so what we're going to do now is try to apply these ideas on the visual data, and we're going to look at the motor response. So the button press, so we're going to define epochs based on the fact that the subject pressed with the right hand or the left hand, and see what is the accuracy we have using a linear SVM in the prediction of if the subject pressed right or left. Okay. So the input of, let's start and I'll maybe give more explanation on the way. So what you need to do is extract epochs. So now you're fluent in extracting epochs, so you need to define your raw file. Then you read your raw file. Okay, then you need to read your trigger channel to know what's in your data. You can plot the paradigm. So that's the very first part that we've done also on the second day. How do you define your epochs? So now we're interested in the response. So the triggers for the response are 14 and 24. And for each of these epochs, we're going to look at 300 milliseconds before and 500 milliseconds after. And here, I'm going to baseline a bit at the before this to avoid any preparation effect. And this is my rejection threshold. Here I'm only going to use the gradiometers because I'm going to use a rather low level function that are not aware that gradiometers are in femtotesla or Tesla per meters and magnetometers are in Tesla. So to avoid any scaling problem, I'm just going to use the gradiometers, and you will see that it's really enough to predict well. And at the end I have my epochs, and you will see that this I've got 111 epochs, okay, and 62 on the left button and 49 on the right button. So it's a rather limited number of trials. I mean, it means that at the end of the day we'll have 100 observations, 100 trials to predict. So the rejections are mostly due to blinks. So now to get a sense if it's likely to work, even starting to do an SVM, what you can do is just a contrast between your two ERF. So right now we're going to use the ERF to classify. There's no change of representation by going the time frequency domain. We're just going to classify based on the time course of each of the gradiometers during the epochs. Okay, so I'm going to define 3 evoked variable. So the evoked for the left response by taking the epochs restricted to the left and then averaging them. So I'm going to have evoked left, evoked right, and just the contrast, which is evoked left minus evoked right. And then I can plot the 3 event-related fields on my gradiometers. So I see the effect of my baseline, and this is the ERF, rather noisy. This is the ERF in the left response. The right response, so I would say like this, is really hard to see if there's a difference, but now if you subtract the two, you have this ERF, okay? So it's still noisy, but you can guess, but just by looking at this, you still have some huge deflection from the baseline. So if you contrast the responses from the left hand or the right hand, the event-related field should reveal an effect around these latencies. Okay, so this cannot be noise. Okay? It's really 3 times the standard deviation of the baseline around. So you can look at the topography of the left condition, right condition. So typically looking at this, you suspect that you have an effect, you don't have a p-value, you don't have a statistical quantified measure of significance, but that gives you a hint that the linear classifier is going to be able to classify something. And what the classifier will do is try to combine the discriminative power of this bump and this bump to classify, okay? That's a fundamental idea in the multivariate approach, is that you use all the channels and all the time points, and if there's a weak effect at the beginning of your epoch and a weak effect at the end, you can combine the two, even though they are very far apart in time, to discriminate your two conditions. So this is just the topographies by combining the gradiometers, where you see on the difference there you have a first difference about 30 milliseconds after the response, and a tiny later one.
This will be above the. This will be on the right side. We'll see it right now in the early.
So this is the left response. Okay, so this is like the like contralateral. This is the right response, so it's more on the left, but not that obvious. And this is just the difference.
Why are they always positive?
Well,
Like
because it's combining the gradiometers. You basically take the norm of the gradiometers, of the planar gradiometers.
Actually, an interesting feature is that here it also seems to be the difference also more towards the right, which was had in the time frequency representations in the statistics hands-on. So we would not necessarily expect Daniel to be perfectly symmetric, but it might also have been a case that Daniel was sitting slightly more towards the right side of the helmet than towards the left side of the helmet, so that's just a difference in physical distance of his cortex towards the sensors, right?
Okay, so the first, like this item number 15 is rather important. If I give you 100 trials in condition A and 100 trials in condition B, and they are completely, so the same number of trials in condition A and B, and I give you this data and say, can you predict which one is A, which one is B? If you flip a coin, your chance level is 50%, okay, because it's completely balanced. Okay, if you predict randomly A or B, then if for the 200 trials with 100 of class A and 100 of class B, on average you'll be at 50%. Obvious? Now if you're in the data set like an oddball condition where you have 80% of condition A and 20% of condition B, what is your chance level? What would be the accuracy of a very dummy classifier?
80%.
80%. The dummy classifier would not even look at the data, it would always predict A. Since they're 80% of A, you'll get 80% accuracy, not even looking at the data. Okay? So if you are in an imbalanced setting, your chance level is not 50%, but the fraction that corresponds to the class that is the most present. It turns out that classifiers and all the machine learning approaches like when the data sets are balanced. There are ways around it to cope with ill-balanced problems. Here, what I'm doing here is just dropping some epochs that are coming from the conditions where there are more trials. Okay.
And dropping them randomly?
So what this function is doing is trying to drop epochs. So it's kind of a smart way of dropping epochs. If there is, if you have AB, AB, and then A, B, it will drop an A in the middle. It tries to balance and also keep the trials as close as possible. So the pairs are also close in time.
Cool.
So if you blink during A and the next trial is B, it will drop the next one. Okay. Okay. So an SVM is completely blind if you feed in fMRI or if you're feeding MEG. Okay. So what an SVM algorithm takes as input is basically a list of arrays or list of points that describe your observation. Here are your trials. So the input of the SVM will be a vector of size 306 times the number of time points, and that will be describing your trial. Okay, so that's a huge vector, 306. So here I'm only using the graduator, so it's going to be 204 times the number of time point of interest. Okay, I'm going to take a time window and use this to predict. Okay. So what I need to do for the SVM to work is take my 3D data, which are epochs, channel, and time, and convert it to something that the SVM can understand, which is trials, and the number of columns will be the number of channels multiplied by the number of time points. Okay. The input of an SVM is 2D. Number of observation, number of features. Okay. Here are features that describe a trial is a channel and a time point. Okay.
Just out of interest, could you, the features, does it matter which way you organize them? You don't have to have first one channel, then all its time points.
Yeah, it's blind to the order of the features.
Yeah, great.
Okay. So the standard notation for a classifier or a machine learning algorithm is the input is called X, and what's supposed to predict is Y. So I will learn from X and Y. I will learn from data and their labels. And now if you give me new data, I'm going to predict the labels. And then I can compare what the algorithm predicted and what I know from the observation and see if it matches. Okay, so here X, the input, is the MEG data. Y is going to be 0 if I'm on the left hand and 1 if I'm the right hand. So the SVM is going to take my graduator data, and for each of these trials 0 or 1, learn from this, and then if you give me new data, it will predict 0 or 1. And the accuracy is going to be how many times in your prediction you predict 0 and it was really a 0, or you predict 1, it was really a 1. Too abstract, confusing, too slow. So here in this line, I'm going to use a classifier, which is an SVM for classification, because you can also use an SVM for other things. So I'm going to use something that's called SVM classifier in this library that's called sklearn, which is it's called scikit-learn. You can just look on this website and read the tutorials and to understand what's happening. So I define my classifier and say C will be like the lambda of the SVM. The SVM has a regularization parameter. This is the equivalent of the lambda of minimum norm for an SVM. And I will use a linear kernel. Okay, it's kind of like the default parameters of the SVM. And then I'm going to use a Monte Carlo cross-validation. So what it means is, in this syntax, 10 times, I'm going to take 20% of the data, remove it from the data set. From the 80% remaining, I'm going to fit my SVM, learn from it, and then I'm going to give the 20% of the data I left out, and I will ask the SVM, can you predict where are the left trials and the right trials? Okay. And here I'm going to do it 10 times. Okay. So what I'm going to get at the end is 10 classification scores, which are for each of the times I left 20% out, how much I was above 50%, if I was. I don't know what this means.
Does that collapse a rock curve into sort of like one number, or is that, am I totally wrong?
The rock curve will be a metric of accuracy.
Yeah.
Here, the accuracy will just be the percentage of time I predict correctly.
Okay.
Okay, just 0, 1.
What's the point of the separation to 80% and 20%? Does it
So-
basically, of course, there's the risk of overlearning if you have the set of learning too high. Or
So let's say if the test size is too big, it means that the number of points I have to learn is too small. So you have a trade-off between keeping enough data to learn,
Yeah.
and also have enough data to validate to have an accurate and robust estimate of your prediction accuracy. So this 20% is usually a good trade-off. You're laughing about the 42?
Yes.
Jesus.
That was a geeky one. Yeah, okay. If you change this, it doesn't work. The whole tutorial doesn't work.
So if you're going to, so you would just do it at one time because you're doing 10 tests, right? And then you're doing 10 splits.
Yeah, I'm going to do 10 splits.
Yeah.
So what I'm going to get is 10 classification scores.
Is there any idea in then running it with another random state and then compare?
We can try.
I mean, should you just,
Let's.
I mean, how many random states should you look at before you can trust your data, or is that
No, I mean,
just one?
typically you fix the random state to have something reproducible.
Yeah.
Okay, so if the value you report in your paper is the value that you get, but you should definitely change this random state, and if your conclusion change with the random state,
Then it's not good.
you have a problem.
Yeah.
That is, by the way, that's also something for the clustering and for the permutations. In this example, we use 1,000 permutations, but depending on the number of permutations that you use in clustering statistic, you have a certain accuracy of the p-value that you're computing. So if your p-value is 4.9%, and it's smaller than 5%, but it's still very close to 5%, and if you then rerun, the next time it might be 5.1. So one of the outputs is also the confidence interval of the p-value. And if you're not sufficiently confident about the p-value, you should just increase the number of randomization.
So here I just rerun this, and we can look at the classification score that we have for the 10 different folds. Okay, so the first fold was perfect prediction, 95%, 95%, 985, and blah, blah, blah. So this is all the values that you got for each of the folds, and you can take the mean value, and this is going to be your accuracy at how much you can predict on trials that you haven't seen for learning.
This is not on the website, is it?
It should be.
Yeah, it is. You have to probably refresh your browser.
Okay. I think I did that.
Okay. So remember this value of 83%. Now there's some.
Somebody surprised about 93%. It's pretty impressive. Yeah,
It's a rather strong response.
yeah.
It's a rather strong response.
So given we could, it's a very consistent brain.
Yeah,
Very
great. It's a
strong
great brain. Great brain.
Great brain.
Yeah.
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 Okay.
At least the right hemisphere.
So there's something that we can test now to see how much the multivariate, like Kung Fu, is actually helping, is run exactly the same thing, but every time point. So now we're going to look at the decodability of left versus right at every millisecond. So basically rerun the cross-validation for every time point. It's like testing, doing a test at every time point of how much we can decode. And what you hope to find is a classification. Now what the output is going to be the classification score over time. Okay. So this is what this for loop is doing. I'm going to do a loop over a time instance, run the cross-validation, and this is what you see in the output. So here I display the classification score and then the standard deviation of over the 10 folds. And so you can see in dark blue the classification score you have. And you see that you're roughly around 50%, so around chance level during baseline, and then after the response, that's where you see the effect. Okay, and you have basically the two bumps that we were just looking at doing the contrast of the ERF, the first bump and the second bump. Now, I also displayed in green the 93 accuracy that we had by combining all the time points. And what you see by decoding only time by time, you basically never reach the accuracy that you get by combining all the time instants. Okay. So it's really by combining all the time instants, by using this multivariate, like MVTA, multivariate, no, MTPA, multi-time pattern analysis, that you basically leverage as much information as you can from the data. Okay. So you in this particular data set, you cannot do better in terms of prediction than the classifier that takes as input the entire trials from 0 to 500 milliseconds. Okay.
Then could you have a sliding window or something?
Yes,
Because if
that
you
would
change
really
the
help.
values-
You could have a sliding window, and this would clearly smooth this curve, and you would have like the curve will be higher and smoother. So you could definitely, if you want to make a nice figure, you should do this.
In fMRI analysis, that's usually done with it's usually referred to as a spotlight approach.
Yeah.
So
Yeah.
where a group of neighboring voxels is used to the classification, and then when the spotlight moves over the whole brain, means that you can still make a picture in which you show the distribution of classification accuracy.
So yeah, it's kind of, rather than doing a spatial searchlight, we do a temporal searchlight. Okay. But one remark I should do is that here I'm basically doing a test at every time point. Okay, so take this decoding as a non-parametric multivariate test. Okay. Okay, so if I do, I'm here doing a test at every millisecond. So just by looking at this, I mean, you should be careful in terms of basically what it gives you in terms of p-value and conclusions. Okay, so if you basically want to do get a p-value of I can decode using something like this, you should permute and do a kind of max statistic by cross-validating over every time point. So you have like ways around this, but this is more for illustration purposes. Whereas the first classification score of 93%, you can permute the targets and see if you can learn as well by basically shuffling the trial values. Okay, it's really similar ideas to the non-parametric approach.
So you're just saying that you have a multiple comparison problem.
Yeah, there's a multiple comparison problem when you do this. And in the searchlight, even though it's never said, that you have the same problem. When you have this ball that goes around the entire brain, you're doing a test everywhere, and you don't control for the false positives. Okay. Now there's something pretty cool that you can do with classifiers, is since you can predict on new data, you can also predict on new time points. So let's say you have a question, is the topography or the spatial pattern at one time point responsible for the discernibility of my two conditions at a later time point? So can I learn at one time point and decode at a later time? There's something that we call time generalization, and so the idea is rather than testing on the 20% trials at the very same instant, you're going to test on the 20% of left out trials at another time point. And what you see is something like this. So here the number of data points is not that high. But here what you can see is,
Put it up a bit.
yes. Can make it bigger. So one line is the decoding power when I learn on this particular time point. Okay. So let's say when maybe I can go here. So if I learn at 100 milliseconds, around this 100 milliseconds, for the various time points around this thing, I can also predict pretty well. It basically means that the pattern of activation is rather stable in this time window. Okay. And the same applies here. Now what you can see is that here it's not red. Okay. It means that the pattern the discriminative pattern from here is not the same one from here, otherwise it would be red here too. Okay. And here you have this huge block here, which basically means that on this time interval, it's likely that you have a rather weak but constant pattern that discriminates the two conditions.
So there's a constant predictability over time.
It's the predictability over time. It's
So that would correspond to late, slower components probably, right?
Yes,
And
yes.
the first one would be the quick 50 millisecond
The quick-
response.
Yes. And basically, if you have something red that turns blue, it basically means that corresponding to your hyperplane, the condition A went from one side to the other and vice versa. Okay. So basically, if it means that if your topography goes from positive to negative, you multiply the topography, the discriminative topography by -1, you're going to flip the points on the other side of the hyperplane, and rather than predicting above 50%, you're going to start predicting under 50%. So what it says here is that roughly the spatial pattern that is useful to discriminate at this latency is maybe on the opposite side as the spatial pattern that is used to decode at these early time points.
And here you're not facing the multiple conversions problem as in the spotlight,
Searchlight.
searchlight.
Somehow, yes, it is still the problem that you have, you do a test at every time point. So if I wanted to threshold this, I would have to do something extra.
Okay.
Yeah. There's no threshold here. Just give you an idea of what's in your data.
So but false positives, do they increase the subsequent probability of another false positive, or is that not necessarily?
I mean, if I have a false positive locally, is it likely that I will have the same false positive?
Because it's like training on that one as well, or?
The training is done at every time point.
Okay.
But now, if you filtered your data, you have a strong correlation between neighboring time points, and so if the data will not change that much, so the classification should not change that much too. So I think that the decoding, I mean, maybe the take-home message that decoding methods are really powerful to find effects in your data. They not necessarily tell you where it is and what it means about the brain, but it's a very powerful way to test if there is anything of interest in it. That's typically something that I tend to use these days. If you give me data and you're interested in two conditions, if a linear SVM on scale data is at 50%, then I'm immediately very pessimistic about the ability to find any discriminative power between the two conditions. Or it means that the information of interest is not in the temporal data. It might be in the power of certain frequency bands, and then you can basically bypass your filter, go into the frequency domain, feed this frequency domain information into the SVM. If the SVM is capable of discriminating based on this frequency band, then it means that might be something to look for. So in terms of statistics, sometimes, who knows what an omnibus test is? Okay, so it's like an omnibus test. Okay, an omnibus test would be testing if there is an effect in your data. Okay, the null hypothesis is that none of my tests are positive, and rejecting the null hypothesis would be there is at least one test for which I should reject the null hypothesis. And it's kind of to me, I like to present the decoding the same way.
So it's very liberal in that way.
Yeah, it's basically there is something in your data, but it does not necessarily tell you where. And basically this idea of searchlights is giving you an idea. But if you want to draw some significant value or get quantified performance based on this, you need a statistical layer on top of it. But typically, if you predict on 100 new trials and your chance level is 50%, you can do very simple stuff like saying predicting 100 values 0 or 1 with 50% accuracy is like flipping a coin. Okay, so if you predict accurately on 90% of the cases, what is your chance of getting 90% of the time heads and 10% tail when you flip a coin where the chance level is 50%. So you can derive a p-value by thinking like this.
If you would write this down into an article, you would probably start by showing the first
Yes.
95%,
Yes.
and then using the rest, so that will be your proof.
Yes.
And then you would use the next two plots you show to investigate what aspects of the signal actually cause this high performance.
Yes. I would do it in this order, basically. And so maybe a final word. So we've used the linear SVM because it's people like SVM. I don't know why. But you have like hundreds of ways to classify things. Okay, there are many classifiers available on the market. SVM are just maybe the most common in neuroscience. There's a huge literature on BCI system, on brain-computer interface. Typically, SVM is not what they use at first. They use pre-processing, things like what we call common spatial filters. So maybe the take-home message, if you really look for performance and not claiming something about there is an effect in my data, if you're really looking for classification accuracy, you have much more clever ways of boosting the performance. Okay. So basically the 93% is not the best you can do, certainly. Okay. Yeah, so if you want to do this at home, I gave you a bit an exercise to answer this question. Can you do better using what BCI people call common spatial patterns? Questions?
Is there a
Yes.
way to understand how the classifier, once you have a trained classifier, what it actually is doing to the data to give you the good classification?
It's a controversial question. You can, because you have a linear classifier. So you can actually look at what the hyperplane is looking like. So if you can open the box of an SVM, and it somehow makes sense to do it, but you need to control what you're doing, and you should make sure that the pre-processing allow you to do it. And because typically the spatial pattern that discriminates the two conditions is likely to look like a dipolar pattern or something with two dipoles in opposite direction, which is kind of a mix of the first answer, the second answer, the first evoked response and the second evoked response. So you could look into it. Now the question is how much you can make a story from what the SVM gives you. It's another problem. Okay. Yes?
What kind of classifier is better for a small amount of data or big amount of data? Because there must be a difference in some.
So all the classifiers are pretty suffering from the same problems, what we call the curse of dimensionality, which is if you're in a huge space and you don't have a lot of data, basically the space is empty and you're trying to make a conclusion from very limited amount of points in a huge dimension. So if you have very little data, you should try to reduce the dimension of your data. And then if you're in low dimensions, things are usually easier for all the classifiers. But for example, I would say it depends if you have unbalanced data set, some classifiers are better than others. Yeah. So there's no clear and obvious answer to this case, because if it works well with limited amount of data, it can only work better in high dimensions. So basically, the classifier that works best with limited amount of data is likely to also stay best for more data. Yeah. So you can try with.
does.
Yeah, so you can try changing the seed from top 42 to your favorite number and see if it works too.